Okay, for what we are going to be looking into is equations quadratic in form. And by definition, equations quadratic in form are equations that have at most two expressions in the independent variable. And if there are indeed two such expressions, then the higher order expression is twice the degree of the lower order expression. And examples of equations quadratic in form, and we have among these, we have for the first, we have x to the fourth plus 3x squared plus 5 is equal to 0. And if you notice, in the case of the comparison of the degrees, so you had the higher order expression is fourth order in x, lower degree is second order in x. So we have for the ratio here, we have 4 over 2 is equal to 2. And we can say that for this equation, this is going to be quadratic in the lower degree of the variable. And for what we have, in this case, we have this to be quadratic in x squared. Another case of what we have to be quadratic in form is going to be what we have with 2y to the 8th minus 3y to the 4th minus 19 is equal to 0. And higher order expression we have at 8, lower degree we have at 4. And again, so you have a 2-to-1 ratio, and this equation would be regarded as quadratic in y to the 4th. Now, for what we have in the third case, we have 7x plus 5 times the square root of x minus 22 is equal to 0. And as a non-integer exponent, the square root of x is x to the 1/2. And just for what we have in this case, we have a ratio of 1 to 1/2, and that is a 2-to-1 ratio. And with the lower power represented by x to the 1/2 or the square root of x, we can say that this equation is going to be quadratic in the square root of x, which is also at x to the 1/2. Now, a case of what we have for equations that are quadratic in form, we have x to the 4th minus 16 is equal to 0. And now for x to the 4th, if I were to factor out equal degree expressions that will multiply into x to the 4th, we have not just x, but x squared. And for minus 16, we have x squared plus 4 and minus 4. And in the real integer coefficients, now I cannot factor a sum of squares, so I still have x squared plus 4. Now for x squared minus 4, I have the option of factoring, and if I do so, we have going out furthermore to the quantity of x plus 2 times that of x minus 2. And if we look at taking each of the factors and setting to 0, so we have with x squared plus 4 is equal to 0. And if I take away 4 from both sides, now we have x squared is equal to negative 4. And we have with the square root property of equality, we have x equal to plus or minus the square root of negative 4. And in effect, we have x is equal to plus or minus 2y. So we have two complex solutions. Now for x plus 2 and x minus 2, if I set each of these factors to 0, so we'll have x at negative 2 and x at positive 2 respectively. So we have altogether, we have that x, again, we have 2i and negative 2i, and also 2 as well as negative 2. So we have four solutions for x, upon which we have x to the 4th minus 16 is equal to 0. Now, second case, we have x to the 4th plus 2x squared minus 8 is equal to 0. This equation, again, is going to be quadratic in x squared. And if I factor out, once again, x to the 4th, so I'm going to have x squared and x squared, and factors of negative 8, whose difference will be on the plus side at 2. So we're going to have x squared plus 4 and x squared minus 2. And now, if I look at factoring and then applying the zero product property, okay, now I have x squared plus 4. I can set this equal to 0. And if I look at x squared minus 2 is equal to 0. All right, so now 2 not a perfect square number. And if I were to factor as the difference of squares, I would have like x plus and x minus the square root of 2. So let's say that for x squared plus 4 is equal to 0. And we have x squared is equal to negative 4. And once again, applying the zero product property, or I should say the square root property of equality. So you have x equal to plus or minus the square root of negative 4. And from this, I have plus or minus 2i. For x squared minus 2 is equal to 0, if I add 2 to both sides, we have x squared is equal to 2. And we have 2 real irrational roots. And in this case, we have plus or minus the square root of 2. So we're going to have, in effect, for x, we have 2 complex solutions with 2i and negative 2i, and 2 real irrational roots with square root of 2, and the negative of the square root of 2. Now let's say that for what we have as a third case. Now I'm going to keep the coefficients. And if you notice, okay, we have for x cubed plus 2x to the 3 halves minus 8. Now this equation is going to be quadratic in x to the 3 halves. And taking what we have here, so if I factor, and notice we have negative 8 as the last coefficient plus 2 as the middle. And if I look at applying what we have in this particular regard, okay, so you have x to the 3 halves plus 4 quantity, and I have x to the 3 halves, and that is going to be minus 2 is equal to 0. And so for what we have in this particular regard, okay, so if I apply the zero product property, so you have x to the 3 halves plus 4 is equal to 0, and we have x to the 3 halves minus 2 is equal to 0, and we have in this particular case, we have x to the 3 halves is equal to negative 4. And for x to the 3 halves minus 2 is equal to 0, I have x to the 3 halves is equal to positive 2. And rewriting what we have as a radical, we have the square root of x cubed is equal to negative 4. And we have the square root of x to the third, okay, is equal to 2. And just taking what we have now, this is a little bit tricky. But we got the square root of x to the third is equal to negative 4, and because of the negative, and since we have an even root radical, okay, we have for this particular part there is no solution, okay, because of the principal square root rule, which states that an even root of an expression cannot reduce to a negative value. Okay, so we have no solution here because of the principal square root rule. Now for what we have in terms of the next part here, okay, and we have the square root of x cubed is equal to 2. Now 2 is a positive constant, so I still have some real estate to work with, and so I can get rid of the radical. In this case, I can square both sides, and upon doing so, we have x to the third is equal to 4, and for what we have in this particular case, if I take the cubic root of both sides, and what's going to happen here is that we have the cubic root of x cubed goes to x, and the cubic root of 4, this cannot be reduced any further, and so there is one solution for x, and only one, and that is going to be the cubic root of 4, and that will fit into this third equation. Now, for what we have in the case the fourth item, again, I'm maintaining the use of the same coefficients. Now this equation is going to be quadratic in the square root of x. And if I look at factoring, say having x go to the square root of x times itself, and we still have the same constants. You have factors of negative 8 whose sum or difference will be at positive 2. And if I look at taking what I have in this particular situation, all right, so you have the square root of x plus 4 is equal to 0, and applying once again the zero product property, I have setting the square root of x minus 2 equal to 0. And if I take away 4 from both ends, so I have the square root of x is equal to negative 4, and I have that the square root of x is equal to 2. And little history repeating itself, have an even root radical of an expression going to a negative constant. And again, you have no solution for the same reason. And for the square root of x equal to 2, okay, so if I look at, once again, eliminating the radical, upon squaring both sides, we have the square root of x squared is going to come out to x, and x is equal to 4. And you can always go back and check. Square root of 4 is 2, 2 times 2 is 4, 4 plus 4 is 8 minus 8 is equal to 0. So we had the solution in this case to end up at x is equal to 4.